is Yong. I'm a third-year PhD student from National University of Singapore. My research interests reside in machine learning applications in geophysics. I'm more than happy to share with you our recent work on 2D to 3D digital rock building using deep neural networks.
Here is the outline. I will start with a brief introduction on our motivations and objectives. Following that, I will share with you two types of methods for 2D to 3D reconstruction. The first one is inpainting using GANs, and the second one is sequential prediction using convolutional LSTM networks. Lastly, I will end this presentation with discussions on our achievements and future work. Let's start with the introduction first. Digital rock physics is a rapidly developing technology that enables comprehensive analysis of rock properties. Its key paradigm is image and compute. As shown in this figure, after imaging the 3D structure of natural rocks, various physical processes are simulated numerically in a digital object to obtain rock property relations. Here, I would like to introduce the imaging techniques to you. As you can see from the figure, from whole core CT, micro-CT to SEM, the resolution increases from 300 micrometers to 1 nanometer. Among them, micro-CT and SEM are frequently used in digital rock physics. As shown in this GIF, micro-CT uses X-rays to image 2D cross-sections of an object from top to bottom and then stack them together to form a 3D image without destroying the original object. As for SEM, it only produces 2D scans of the surface of an object with the focused beam of electrons. Compared to micro-CT, SEM offers enhanced resolution and a larger imaging scale, except that it does not provide full 3D scan. Considering the pros and cons of SEM, I'm sure you will find out one challenge in digital rock physics. That is the difficulty to utilize 2D SEM images. Apart from that, performing full 3D CT scan is very expensive and time-consuming. So, what if we can reconstruct 3D rock images from limited number of 2D slices? Conventionally, people will use stochastic method, which provides multiple realizations of 3D digital rocks. However, the reconstructed images are too simple to capture the complexity of natural rocks. Since we are dealing with large number of images, why don't we turn to deep learning, which has been a game changer in computer vision? If deep learning succeeds in this task, there actually comes with another thrilling benefit in addition to saving imaging cost. That is, the well-trained neural networks also extract features from digital rock images, which can be effectively exploited in other tasks, such as rock classification or image segmentation. It's time to talk about the first method, inpainting using GANs. Suppose this cube is the 3D digital rock we want to reconstruct. It is scanned layer by layer along the z-axis. The yellow section in the middle is skipped to save imaging cost. This is how the rock is visualized from XY perspectives, either complete slices or empty slices. If we view it from wider perspectives, it becomes incomplete slices with missing stripes. So the aim is to restore the missing structures using GANs. After inpainting, those inpainted slices are concatenated to recreate the 3D digital rock. Please note that this method assumes the rocks are isotropic. That's why the neural networks can learn structural information in XY domain and then transfer it to YZ domain to fill the missing part. Now let me walk you through the inpainting workflow. The first step is to train a generative adversarial network, or GAN in short, to produce fake 2D scans that can fool human eyes. GAN consists of two competing neural networks, namely the generator and the discriminator. The generator takes random noise vector C as inputs and outputs synthetic images. The discriminator takes both the real and generated images as inputs and tries to tell fake images from real ones. The generator is trained to fool the discriminator, while the discriminator focuses on learning to distinguish real and fake data. Under such adversarial training scheme, the generator will slowly produce fake images that can fool human eyes. Next, an autoencoder is trained using real images, synthetic images given by the generator of the GAN, and masked images. Note that masked images are real images with random stripes masked with zeros. An autoencoder is composed of an encoder and a decoder. The encoder compresses input images to a lower dimensional hidden space Z', and then the decoder will restore the image from the hidden space. The loss function has three parts. There are reconstruction errors for real images, synthetic images, and masked images. The reconstruction error for masked images is named as inpainting error because it measures the difference between the reconstructed image from the masked image and the real image before masking. Hence, this autoencoder also does the inpainting objective. However, the inpainting results given by the autoencoder do not have high resolution. After pre-training, the generator of the GAN and the encoder of the autoencoder are combined to form the generative encoder, which offers high-resolution inpainting results. The inpainting problem can be solved by solving this function. X tilde is the image to be inpainted. It is mapped to the hidden space Z' using the encoder. The synthetic image given by the generator is masked by the masking function I and then mapped to the same hidden space Z'. This objective function aims to minimize the difference between the reconstructed image and the masked image in the hidden space learned by the encoder. The reconstructed image X hat is produced by the generator with the soft optimal Z hat as input. To conclude, the key idea of this method is to train the GAN and the autoencoder separately for different objectives. The GAN is trained to generate realistic rock images, while the autoencoder focuses on learning inpainting. They are integrated into the generative encoder to solve for high-resolution inpainted images. We test this inpainting method on microcity images of a dry sandstone outcrop published on the Digital Rock portal. The reason we use sandstones is that sandstones are always isotropic, which complies well with the isotropy assumption of this method. Each image in this dataset is cropped to size 256 by 256 from the center. Here are the inpainting results for some testing examples. Values within the red frames of the original images are masked with zeros. The reconstructed images are shown next to the original ones. Overall, most of the structural information are generated successfully after inpainting. Let's zoom in for some finer details. It seems that the reconstructed images are smoother and miss some finer grain details in the original images, such as these narrow pores. This might be related to the fact that the autoencoder focuses on generating coarse general structure and prefers smoother images. After concatenating all inpainted slices, the concatenated layer viewed from XY perspectives is shown on the right. The ground truth is on the left. The good news is that some trace of the pores, especially large ones, can be observed from the concatenated layer. However, the reconstructed images loses the connectivity and the continuity of internal structure. In future work, we will adopt some post-processing techniques to improve the connectivity of the concatenated layer. Apart from that, adding connectivity constraints in the inpainting workflow is another approach worth trying. Next, I will share with you another reconstruction method, sequential prediction using convolutional LSTM networks. In aforementioned method, we try to fill the gaps between parallel 2D slices by inpainting. What if only a short consecutive sequence of 2D slices is given, or the rocks are no longer isotropic? Under those conditions, the reconstruction problem becomes a sequential prediction problem, which aims to predict the most probable following sequence of slices from the given sequence of slices, as described by this equation. There are two crucial aspects. One is the spatial correlation in XY plane, which can be well handled by convolutional layers. The other one is the image variations along the axis. This can be handled by recurrent neural networks. Therefore, we build our neural network based on the convolutional LSTM layer, which integrates the 2D convolutional layer into the LSTM layer. In the following part, I will introduce the structures of convolutional LSTM layers to you before we go to experiment part. Long short-term memory networks are a special kind of recurrent neural networks that is capable of learning long-term dependencies. This figure shows a standard LSTM layer. It takes sequential inputs xt and output sequential hidden states ht. The output from last time step is taken as one of the inputs to current time step, as depicted by these red arrows. Hence, ht is called short-term memory, which only carries the influence of last sample. Ct is the cell state at time t. It runs straight down the entire chain. Hence, Ct carries long-term memory. Now let's walk through the LSTM unit step by step. The information flow within the LSTM unit is controlled by structures named gates. A gate is a dense layer with sigmoid activation function. Each element of the output of the sigmoid layer is between 0 and 1, describing how much of the input component should be let through. As shown in this figure, the gated output equals the pointwise product of the gate and the input. At time t, the previous hidden state ht-1 and the current input xt are concatenated and taken as input to the dense layer with the hyperbolic tangent activation function to calculate the modulated input. The same input is passed to three separate sigmoid dense layers to obtain the forget gate, input gate, and output gate separately. The forget gate and input gate are applied to the previous cell state Ct-1 and the modulated input Ct tilde to decide what to discard from the long-term memory and what to add from the current inputs to the long-term memory, respectively. With a simple summation of the preserved memory and the current input, the new cell state is obtained. The new hidden state is updated along with the new cell state, with the output gate to regulate the final values. Remember that all gate states, inputs and outputs of a standard LSTM layer are vectors. Although images can still be input to LSTM layer after flattening, the spatial information is totally missed. In order to adapt the standard LSTM layer to be applicable to image data, the convolutional LSTM layer was proposed with two main modifications. First, all inputs, gates, cell states, and hidden states are extended from 1D vectors to 3D tensors. Second, the dense layer used to compute the gates and modulated inputs is replaced with 2D convolutional layer. The integration of convolutional layers and LSTM layers enable the convolutional LSTM to handle spatial temporal information. Now I'm going to talk about our experiment on microcity images of a carbonate sample from the Digital Rocks portal. Before training, all images are split into patches of size 256 by 256, as shown here. This is the structure of our neural network. It is inspired by a popular variant of autoencoders named UNet. The U-shape and the concatenation operation of the original UNet are kept, with the 2D convolutional layers replaced with the 2D convolutional LSTM layers. Note that the orange arrows represent state transitions between successive time steps. The network is trained to predict the next slice from the input slice, and the length of input sequence and output sequence is both 5. The loss function is the L2 norm of the difference between predictions and the ground truth. Here are the training results of one test example. The neural network predicts slice 2 from the input slice 1. The prediction error on slice 2 is not very low. This is because one input image does not provide directional information. The neural network is not sure about which adjacent image to predict, either the one to the right or the one to the left. Now with one more input slice S2, the neural network infers the direction of the slice sequence. Therefore, the prediction error on slice 3 decreases significantly. With 3 input images, the prediction error on slice 4 decreases more. Let's keep going and flip back repeatedly. It can be observed that the prediction error stabilizes after slice 1, 2, and 3 are input to the neural network. Apart from that, the stabilized error is randomly distributed, demonstrating itself to be the random noise in raw microcity images. Therefore, the neural network is able to remove random noise. Here we test the performance of sequential prediction with 2 known input images, S1 and S2. S2 hat and S3 hat are predicted slices. As we just discussed, slice 3 is accurately predicted with 2 given previous slices. Later, the predicted S3 hat is taken as the next input. The generated S4 hat is very smooth, and the prediction error is very high. As the iteration goes on, the predicted images become too smooth to reflect any structural change along depth. Overall, only one next image can be accurately predicted given 2 known consecutive slices. Again, the smoothness of the generated images impedes 3D image reconstruction. Now comes the discussions. We propose 2 types of methods to realize 2D to 3D digital rock reconstruction. The preliminary results are very encouraging, but we still have a lot of space to improve. As for the inpainting method, the general structure of sandstones can be well reconstructed along the inpainting blocks. However, the concatenated slices viewed from other perspectives lose the connectivity and continuity of rock structure, although some trace of pore space is there. So for future work, we plan to improve the autoencoder to enhance the resolution of inpainted images, such that fine details can be recovered. We also want to post-process concatenated layers to improve the overall continuity of 3D rock structure. Lastly, we are considering adding connectivity constraints into the inpainting workflow. As for the sequential prediction method, the convolutional LSTM unit can accurately generate the next slice from at least 2 given slices. As a type of autoencoder, UNet can remove random noise and thus produce smoother results. However, this denoising function impedes the performance of sequential prediction. As we wrote here, the predicted images become too blurred to view any structural details very quickly, as more smooth predicted images are taken as input image recurrently. So for future work, we plan to either add noise back to the predicted images by adding random noise into intermediate layers of the convolutional LSTM unit and let the network learn to carve the noise, or remove random noise from the training images using wavelet transform or curvelet transform. Moreover, we plan to downsample training sequences along depths to augment change between adjacent slices. That's the end of my presentation. Thank you very much for your time.